there's a bunch of different ways that you guys might see this displayed. So I tried to do several different examples here with different displays, but a lot of ways when you have conditional probability, it'll be from what they call a contingency table. And forgive me, this kind of printed weird, but it's a two-way what they call frequency table. And it can be more than two categories. This one is just a small example. So the two categories, ladies, thank you. Okay, right-handed or left-handed, male or female. There can be like 3, 4, 5 categories. It doesn't have to be strictly two, but this is just a small example. Now, really the data that you need, I'm going to grab a marker here, hang on one second. Okay, sometimes the tables don't give you the totals. Sometimes the tables will just give you small amounts of data, like they give you 43, the 9, the 44, and the 4. That's typically a contingency table. It's useful to know the totals to help you do the probabilities if you have to calculate them. Okay, so just to see if you guys can read the table. Can you look at this? And this is just looking at the table. How many people total are represented in the table? 100 people. Okay. 87 people are right-handed, maybe. Okay. How many people in that table would be female? 48. So across this row right here, the total, 48. How many people would be male? 52. What about how many people would be right-handed? 87. Okay. And how many people would be left-handed? 13. Okay, so you guys can read this. All right. Now, we're going to see if we can do some probabilities here. Tell me, I'm going to scooch this up. Tell me the probability I randomly grab somebody from this table and they're right-handed. 87 over 100. Okay, so there's a total 87 people are right-handed out of 100 people in this table. If you want to just do 0.87, 87%, any of those are correct. Okay, what would be the probability I randomly take somebody from this table and they're female? 48%. It'd be 48 out of the total 100, or 0.48. Okay, now, there's different ways that you can do this. I would just recommend, I do this visually, I don't multiply these together. The probability that they're male and right-handed, I just find the place in the table that fits both of those categories. So here would be male, right-handed, it would be this number right here would be 43. So that'd be 43 out of the total in the table. So 43 out of 100, or 43%. What would you tell me, probability I pick somebody at random and they're female and also left-handed? 4%. So just this one fits both of those. So it'd be 4 out of 100, or just 0.04 or 4%. Any of those are fine. Okay, now, male or left-handed. So this is a little bit tricky, and I'm not even getting this, I'm trying to get it so you can see it on the page. So one or the other. All right, so probability the person would be a guy from this table, you got 52. Probability they're left-handed would be 13. And these are going to be not mutually exclusive. There's an overlap here, right? So when I counted all the guys, that was 52, and I counted all the left-handed people, that was 13. I counted that 9 twice, so I got to subtract off that 9 because I counted it twice. I counted the guys and 4 left-handed. So I'm going to add these guys up, and this will be over 100. So it'd be 56 over 100, or 56%, 0.56, however you want to write it. All right. And then the last one says female or right-handed. So all the females in the table, I've got 48. And all the right-handed people in the table, I got 87. But I got to subtract off any overlap because I counted some people twice. So right-handed was 87. Female was 48. I counted that 44 in there twice. So I've got to subtract that off. So we're going to end up with 91 out of 100, 0.91, 91%, however you would like to write that. Okay. Is anybody having a question about how to do any of the probabilities from the table? I'm going to use that table at the bottom again here, but we're going to talk about a little bit different kind of probability here. Okay, so conditional probability. There's going to be some kind of condition that's given to you. It says the probability that an event B will occur given that another event A has already occurred. Okay, conditional probability exists only when two events are dependent. They have to be dependent. If you're seeing one of these tables, there is no independent event. They are dependent on each other in some way. And to write the conditional probability, all right, so this is the conditional probability of event B given that A has already occurred. All right, so this would be written like this, probability, and then just like a little parenthesis, B, and then you have like a vertical line and A. That vertical line just represents given. So you assume that A has happened when you do that probability. Okay, now to calculate this is probability A and B divided by the probability of A. Now, some of these questions I'll use the formula for. Some of them I just kind of do a visual, which is what I'm going to show you to do. And you guys don't need to recopy this or anything, but I'm going to really quick copy the numbers from the table at the top just so you guys can see them on the screen, because I'm going to use them for this example here at the bottom. So this is just from the table at the top. Sorry, I should have just copied the table down here and I just wasn't thinking about it. All right, we got male, female, this is right-handed, left-handed. Okay, now, here's the deal. Whatever you're given, so this first one says the probability you're right-handed given that the person is female. If that's the case, you only want to look at that part of the table. So I'm being given that the person I selected is female. So what would always go on the bottom of the fraction would be the total from that row. Okay, so the probability I picked a right-handed person given that they were female, then you just have to, I know I just covered up the labels for the columns there, but this would have been the 44 out of 48 in terms of what people have right-handedness there. So just divide that real quick. And I'm just going to go 3 decimal places. So it's about 0.917. Okay. Now, this almost looks like the same question. So it says probability that they're female given that they're right-handed. So this is written in a different order, so that does matter. So in this case, I'm being told that I've picked, given that I have a right-handed person. So in this case, I only want to look at that column of the table. So the total number of right-handed people, which would be 87, that's going to go on the bottom. And then female out of that group is going to be the 44 again, but you guys see I have a different number on the bottom because I had a different condition here. So this is going to be 44 out of 87 this time. So this is about 0.506 if I go 3 decimal places. Okay. See if you guys can figure out these other two. I'll just give you a couple seconds to do it. What would you write given the condition? So you got left-handed given that the person is male, and then you've got male given that the person is right-handed. Do fraction, decimal, whatever you like better. Okay. Somebody tell me what fraction or what decimal did you have for left-handed given that they were male? What did you set up? What'd you set up? Sounds good to me. Okay. 9/52. If you're given that they're male, you only want to look at that row right there. So they're male, that goes on the bottom, and then they're left-handed from that category would be 9 out of 52. If you guys want to write that as a decimal, I think it's 0.172. Oh no, did I round it wrong? Fired. Oh, you're right. It's 173. Okay. That's not even close. I can't even say that I rounded it wrong. Okay. What's the probability I pick somebody from this table, they're male, given that they were right-handed? What'd you put up? Yes, ma'am. 43 over 87. And I'm actually going to see what that decimal is real quick. Okay. So like if you did a decimal, 0.494. So just a little bit more than 49% there. Is anybody having a question? Say that one more time. Why we're taking the 53? You mean 43? Oh, for this one, 52? Okay, so given that they're male, so that means I know I did not pick a girl. I picked a male person, it's given that. So it would be only out of those 52. What's the probability then that they're left-handed? So I put the 52 on the bottom, and the left-handed would be the 9 on the top. Whereas this one says it was given that they were right-handed. So I know this is my total, because if I only have 87 right-handed people, I'm being given that I picked one of them, and then probability that they're male here, it's either the 43 or the 44. I picked the 43 because it's the male. So it's that category if you're given that. So it's a little bit different than the probabilities we've been calculating. Really good question. Does anybody else have any question? Okay. Now on the back, you really don't have to do anything up here at the top. This is just a visual that I stole from the internet, if I'm being honest with you. So I thought it was pretty good. But another way you might see something like this displayed is with what they call a tree diagram. Okay, so here's how the tree diagram works. You basically start and you branch off and you make like a little tree is what it is here. So the example that they have here is just if you were to flip a coin. Okay, so if I flip a coin, there's two things that could happen. I could either get heads or I could get tails. Now what they do is you have your starting point. The little arrow is called a branch. They write the probability of whatever's at the end of that arrow on the line. So the probability I get heads would be 50%, so it's a 0.5. Probability I would get tails is 0.5. The outcome is written at the end of the little branch. Don't make it complicated. Okay. I guess that could happen. Maybe if you were in grass or something like that. We'll just say it's on a flat surface, and if that's the case, we would do it over. So it's not going to land on its side. It's either heads or tails, one or the other. When does it land on its side? Have you had that happen?
No, I'm saying there's a probability.
I don't think 0.0001. Okay, well then I guess okay, so then yeah, you could just blow it over so it falls on one or the other. Okay. So we're gonna pretend that we don't land on the side. Okay. Okay. Now, how to calculate a probability from, there's nothing really to calculate from this one. It would just be 50-50. So really it's going to be if a couple different things could happen. So that's what's going on here to the side. So same thing. They just show you probability of heads or tails. And then what's the second round here is then what would happen on a second toss. Okay, the two little branches, so they come out of the same spot, the two branches, the probabilities always have to add up to 1. This is not my greatest example ever, but like 0.5 and 0.5, that adds up to 1. So they have to add up to the total number, 100%. We're not landing on the side, so there's nothing missing there, I promise. Okay, so if I told you, okay, let's calculate the probability that I flipped tails and then I flipped heads. Okay, the way it works in the little probability table. So probability I flip tails would be here, and then I flip heads on my second. You would multiply these together. So 0.5 times 0.5, and then they have these all calculated for you so you can see here. But that would be this one right here, and that would be 0.25. So if you're trying to use a tree diagram to calculate a probability, you multiply along the branches till you get to the outcome that you want. So we're going to make a tree diagram for this example here. Okay, so, and some of these, it just kind of depends on the wording of the question. They might not give you all the information for the kind of the beginning of the tree till later in the question, but this is just kind of bullet pointed here. It says the school system compiled the following information from a survey it sent to people who were juniors 10 years earlier, so 10 years ago. And it says 85% of the people ended up graduating. Okay, so I'm just going to make two little branches, right? All right, so one outcome would be that I graduated. What would the other outcome be? Yeah, like you dropped out, or you, for whatever reason, you didn't graduate. Okay, now it says here 85% of the people graduated, so I'm going to write 0.85. So what would you write for the probability the person did not graduate? Go ahead, what were you saying? 0.15 or 15%. Usually if you guys see these tree diagrams, they'll use decimal versions, but you can use a percentage too if you want. Okay, now my second bullet point says, of the students who graduated high school, 90% are happy with their job. So I'm just going to make another little branch set here. So I'm just going to write happy with their job. The alternative would be that you're not happy with your job, right? So for this example, it says the people that graduated, 90%, so I'd write 0.9 on my little branch there, are happy. So what percentage would not be happy? 0.1 or 10%, yeah. Okay. Now, underneath there's one more bullet point. It says of the students who did not graduate, so we're going to make another little set of branches here. 60% are happy with their current job. So we've got people here that are happy and people that are not happy. 60% are happy with their job. So what percentage of people here would not be happy with their job? 0.4. Okay, whenever you have the two branches that come out of the same little starting place, they have to add up to 1. So like 0.6, 0.4, that adds up to 1. 0.9, 0.1, that adds up to 1. 0.85, 0.15 adds up to 1. All right, so see if you can calculate these. What is the probability that we randomly select one of these people and they graduated and they are happy? So they graduated, you don't have to write this, I'm just going to write it. Graduated and they're happy with their job. How would you calculate that with the tree? Oh my goodness, don't everyone turn out to me. What do you think? Yes, okay. So graduated, we would go along here, so it's a 0.85. And I want to end up with the category with people are happy, so 0.85 times 0.9. And we're just going to calculate this real quick. So we're going to get 0.765 there. Okay. So this next one says, what's the probability a student from this junior class 10 years ago did not graduate? So I'm going to write, they did not graduate and they are happy with their current job. How would you calculate that? Didn't graduate, but they're happy with their job. What do you think? Perfect. 0.15 times 0.6. You just multiply along the branches till you get the outcome that you want. So this would be 0.09. Okay. Now, I'm going to give you, let me just give you one little example that I didn't represent here very well. I'm just going to come back up to my tree. What if I asked you to tell me the probability, I just want the probability, I randomly select a person and they're happy with their job. So I don't tell you whether they graduated or didn't. How would you calculate the probability that I just randomly select a person here, they're happy with their job? Okay, she says 0.9 times 6. 0.6 is, and this is what almost everyone says every time, but there's actually a little bit different way to calculate it. Yes, so this is really weird, so that's why I wanted to give you guys this extra little example. Okay, so happy with your job, there's two ways this could happen. So if you graduated and you're happy with your job, the other way could happen, you didn't graduate and you're happy with your job. So you would actually take these two and you're going to add them together. So graduated and happy with the job, plus didn't graduate and happy with the job, which we actually just calculated both of these values below if you want to just use that, just 0.765 plus 0.09, which we get 0.855. So most of those people, like almost 86% of those people, whether they graduated or they didn't, they're happy with their job. Is anybody having a question? Okay. Now, for this last example, and these are a little trickier when they give you these percentages like this. So I'm going to rewrite the little formula I wrote on the front because I actually might use this in that case. So if you have a conditional probability, so this was the probability B given A. It's the probability of A and B divided by the probability of A. So your given is what has to go on the bottom. Okay, so what I have in this lovely little representation here, this is 39% of people in a survey of some kind have a pet now, and, so you'll see the and here, have had a pet. Okay, 61% of people just don't have a pet, 86% have a pet, and 14% do not have a pet now, and they have never had a pet. Okay, now this says, we're going to find probability here. So randomly chosen respondent has a pet given that they've had a pet at some point. Okay, so I'm going to look in that group. I want the number where they have had a pet or have had a pet. So that's going to be the 0.86. Whatever your condition is, that goes on the bottom. Now, you can write that as 0.86. You can write that as 86%. You can just write 86 if you want. These will all give you the same thing as long as you're consistent. Okay, now, what number out of that group would you put on the top of that fraction? You don't have to subtract anything. You're just going to grab something off of that table. It's the 39. Okay. Have a pet now and have had a pet. So this would be they have a pet, they have a pet. So have and had in the past also, but they have a pet. So this would just be the 39 would go on the top. So you're just literally going to take 39 divided by 86. Or 0.39 divided by 0.86. They would all give you the same thing as long as you're consistent. So this would be about 0.453 to 3 decimal places. Okay, now my last one. Randomly chosen person, never had a pet, given that they don't have a pet now. Okay, so they don't have a pet now, that's the condition, so that goes on the bottom. So I'm going to look through here. Do not have a pet now is 61%, so that's going to go on the bottom. That's the condition. What would you put on the top of that fraction? The 14. Do not have a pet now and have never had a pet. This is right here, never had a pet. This is 14. All right, so it'd be 14 over 61 or 0.14 divided by 0.61, however you want to do it. I'm getting 0.2295, so honestly, if I was rounding that, usually the Math Excel asks you for 3 decimal places. So I'd just go 0.23 for that if it asked me to. Let's not get into sick faces. That's a whole other nightmare. I don't want to do it. Okay. Is anybody having a question?